Right, question 4. I don't think this is a very good question for a number of reasons, which I will whine about during the question. So don't worry about this one too much. So let's just get on with it. Right, it's a question about reaction time. So you've got the ruler and someone's dropping it and the other guy's trying to catch it and react like that. So here are the numbers they give you from the question sheet. And the first task is to calculate the average distance dropped for the right hand here. So we have to fill in that. Well, that's fairly simple. Add up these 5 values, divide by 5, straightforward, stick it in the calculator, and you get 8. So it turns out to be 91.8, those 5 added together. Divide by 5, number of trials, and that is 18.36 centimeters. Okay, this is average distance, and it wants it to 2 significant figures. 2 significant figures is that 3 leaves the 8 alone, so it's 18 centimeters to 2 significant figures. Okay, so let's fill that in there. Okay, straightforward enough. Right, calculate the average time for the left hand. The average time. That was the average distance that the ruler's fallen. Okay, now it wants your average time, and they give you the formula they want you to use. It says use the equation time squared is distance over 500. Okay, so they tell you that's the equation you've got to use. Stick in the numbers. And we have to work out the average time. So I'm just going to call it T and D. Okay, so T squared is D over 500. Therefore, take square root. Time is the square root of D over 500. Okay, so now the distance fallen is 14 centimeters. So it says calculate the average time for the left hand. Okay, so it's this one. So the distance we're going to use is that. It doesn't tell you in the question whether it wants you to put the distance in centimeters, or, as you should normally do in a question, convert everything to meters. Always work in meters, right? But they don't tell you to do that in this question. It turns out you get the right answer if you use the value of 14, not 0.14. So that's not great. So use D is 14 centimeters, 14 over 500. Okay, stick that in the calculator and you get a sensible answer. You get 0.16733 something. We're not going to leave it like that. What's a sensible number of decimal places to take it to? Well, you could, I would say it's quite a short period of time, so let's just leave it as 0.167 seconds. Okay, you could write 0.17 seconds, but which would probably be fine. But this is a very short period of time, so I think 0.167 seconds is sensible. Okay. See, if you did what you should normally do, what you've been taught to do, what you should do in questions like this, you convert distance to meters. Now, if you do 0.14, okay, over 500, which I wouldn't blame you for doing this question. Like I say, you're meant to convert centimeters to meters in formulas, right? Then you get the time that's a time, it's in seconds, okay, of 0.0167 seconds. And like I say, I think it's a stupid question because they don't even tell you where this formula comes from. We'll talk about that in a second. But they should tell you they should tell you that they expect you to break the rules in this question and put D in centimetres, not in metres. If you did put it in metres, you get a reaction time of 0.0167 seconds. So if this happens in an exam, okay, it's a good lesson. Always check your answer. Is it a sensible answer? A reaction time, okay, when you're dropping something and trying to catch it, of about a fifth of a second is sensible, right? So you can see that that's what you should probably give in the exam. A reaction time of a 50th of a second, or less than a 50th of a second, is not realistic. Okay, you're not Superman. So that's why that is wrong. So look at the answer. Is it a sensible value? A reaction time of 0.0167 seconds is not realistic. So that's the correct answer. Okay, enough ranting. Right, so if you're wondering where this equation comes from, it's SUVAT, right? SUVAT is, I don't want to get into this too much because it's not really what this question's about, but it's constant acceleration problems, okay? So constant acceleration means on Earth, when you drop something, okay, that pen is falling under constant acceleration. Its velocity is not constant, its velocity increases, its acceleration is constant. The acceleration on the surface of the Earth due to gravity is 10 meters per second squared, or 9.81 to be a bit more accurate. Okay, so it's accelerating at 10 meters per second squared. Constant acceleration. And this is a constant acceleration question because the ruler is also, when you drop it, the ruler, it's falling at 10 meters per second squared acceleration. So, I'll just show you where this question comes from, this formula comes from. You're letting go of something, U, its initial velocity, because you're holding it stationary, is 0, okay? The acceleration downwards is 10 meters per second squared, okay? Meters per second squared is the same as meters per second squared, okay? We don't care about v, the final velocity. We do care about the distance fallen, that's what we want to know, okay? Sorry, we're told the distance. It's time we want to know. The distance is 0.14 meters, and we want to know the time. Okay. So, which of the SUVAT equations connects U, A, D, and T? In SUVAT, sorry, we use S for distance for some reason. It's not DUVAT, it's SUVAT. So the distance, S, is 0.14 meters. U, A, S, and T, okay, it's S is UT plus half a T squared, okay. U is 0, so U times T, whatever it is 0. So we just get S is half a T squared. Rearrange it, and we get that T squared is 2S over A. 2S over A. See, that's similar to that already. So right, now the acceleration. So T squared is 2S, whatever the distance is, over A is 10, acceleration due to gravity. So T squared is 2 over 10 is S. It's basically S. It's an S, not a 5. S over 5. 2 over 10 is the same as 1 over 5. Okay, so that equation, that's where it comes from. Now, if we were working in meters, which we should be, then that equation would be time squared is the distance over 5. But we're working in centimeters, and they didn't tell you that, like I keep whinging about. If this was, okay, so that's the equation for S in meters. If this were in centimeters, it's a factor of 100 difference. So in that case, t squared, you would write it as S over 500. Because if S is in centimeters, then it's a factor of 100 times larger, the number. 14 centimeters is 100 times, the number is 100 times larger than 0.14 meters, even though it's the same distance. So in centimeters, it's t squared is S over 500. In meters, it's S over 5. It just comes from Suvat, okay? From that. Okay, let's move on. Right. Explain whether any of the readings are anomalous. Let's look at them. Average of 14, 10, 25. Yeah, that one. These, they're all reasonably close to 14. Same here, 18. They're all fairly close to 18. But yes, that one is anomalous because there's a large difference between that value and the average value. Okay? That's it. Right, give 2 ways the students can improve the quality of their data. Okay, another question I don't like. Okay, you've got one guy holding a ruler, okay, and another guy trying to catch it like this. And you measure it, and he's catching the ruler at a certain point, and you're measuring the point where he grabs it. So you're measuring a distance on the ruler. So you can't improve it with stuff like an electronic timer. You're not using a stopwatch here, it's just reaction times. So how do you improve the data for a sort of problem where you can't use any electronic equipment? Well, the first way, okay, remember this for exams, for these sort of questions, is simply to take more readings, right? You've only taken 5 readings here, take 10 or 20 or 50. The more you take, the better the quality of your data. Now, looking at the mark scheme, this is a 2-mark question. For the second mark, it says, say something to do with a third student measuring the time. Okay? So, I don't really know what they're getting at here. Do they mean, see, it's only a 2-person experiment. You don't need a third person. There's no third person with a stopwatch there, okay? It's one person letting go of it and somebody else catching it. So how does introducing a third person make things better? It's not clear to me, but that's what they give the second mark for. So, do they mean have the same person drop it and swap the person catching it for a third person? Well, that would mix the reaction times of 2 people. I don't know. So, don't worry about this too much. It's a terrible question. If you get a question like, I hope they improve it by the time the exam comes around and they don't ask this sort of a question. If they do, just remember, try and say something along the lines of getting a third person involved and measure, I don't know, maybe repeat the experiment with a third person catching it and see if you get similar times, maybe. I don't know. Anyway, should I say more about that? Let's just move on, okay? Don't worry about that question too much. Right. Describe how the students could develop their investigation to investigate how reaction time changes with another variable. Okay. I wouldn't blame you for not really knowing what they're asking about, what they're getting at here. What they mean is just describe an experiment you can do to see how reaction time changes with something such as how it varies with age, the age of the person catching it, or their height, or what they had for breakfast, or how much sleep they got. Something like that, okay? So let's go with age, right? Let's say we want to see how the reaction time varies with the age of the person catching it. So what you do, it's only a 2-mark question, okay? So don't do too much. You don't need to say a huge amount. Something like, choose a large group of students from different years in the school. So you've got a decent range of ages, I don't know, from like 11 to 16, for example. Get 11-year-olds, 12-year-olds, 13-year-olds, 14-year-olds, 15-year-olds, and 16-year-olds. Do the experiment with them, do the calculation to find the time, so you have a set of data. And then you can maybe plot a graph, something like this. So you'd have age along here, so 11, 12, 13, 14, 15, 16, age in years. And here you'd have the reaction time. It looks like it's around like 0.15 seconds-ish, so maybe you'd have 0.1 there, 0.2 there, 0.3 there. And for every person who you've done this experiment with, you'd have one data point. So maybe one 12-year-old had a reaction time of 0.15, so it would be about there. A 14-year-old maybe had a reaction time of about 0.2. And you get a load of data points like this, okay? And you would be looking to see if there's a relationship between them, okay? Maybe the way I've drawn it there, it's kind of slopes up slightly. This is a total guess, okay? That would suggest maybe that as you get older, your reaction time increases slightly. That's just the way I've drawn it there, okay? But who knows? So that's the sort of thing you're looking for, but that's way more than you need to actually write. It's only 2 marks. Just get that sort of thing down quickly, a quick sketch of this in the exam. Okay, I didn't like that question. I don't think it's a very good one. Don't worry about it too much. Let's move on to the next.